So I want to take the inverse Laplace, I want to unLaplace this function. And I see it as a line over a quadratic. And if the quadratic factors, if the bottom factors, then I should break it up into partial fractions. Let's say that the bottom factors into s minus 8 times s minus 7. I would do partial fractions, and then I could unLaplace this first piece to be whatever number a is times e to the 8t, whatever number b is times e to the 7t, if the bottom factors. If the bottom doesn't factor, I want to complete the square. So to see if the bottom factors or not, let's just try and solve it. Well, you know what? I've got down here, I've got the auxiliary equation. So s squared lambda squared 4s 4 lambda 13. And this would be the auxiliary equation, and that would match the bottom here. And if I was solving for these eigenvalues to see if that bottom factors, let's go compute, solve, and I get, complex conjugate eigenvalues, 2 plus or minus 3i. If my solution then was 2 plus or minus 3i for eigenvalues, my solution would look like this. Some constant e to the real part t cos imaginary part t, some constant e to the real part t sine imaginary part t. So if the eigenvalues were 2 plus or minus 3i, this is the sort of solution form that I would think I would get. But now I know the denominator, the bottom, doesn't factor. So our plan was then complete the square. Okay, so I'm going to complete the square on the bottom. So I'm going to take this s squared minus 4, and I'm going to take half of what's in front of the s piece, so half of minus 4 is minus 2, and I'm going to make it minus 2 squared and minus 2 squared. That's me completing the square. If I were to expand that all out, I would get that s squared minus 4s. Now minus 2 squared is 4, minus 4 plus 13 is a plus 9. So now I've completed the square. If I were to expand this denominator out, I would get the same denominator. And now let's see this as, well, okay, let's look at the transforms that I think I need here. That's the form that we think we're going to get. These are the transforms that I think I need. I see something squared plus 9. So if it was an s, so I'm looking at it, if it was s squared plus something squared, cosine if there's an s on top, sine if there's not an s on top. But I see this as, it's not just s squared, it's s minus 2 squared. I need the shifted version of the inverse transform. So let's look at the cosine piece first. If I multiply by e to the at times some function, so I'm matching this piece. It looks like there's an s minus 2. So matching this piece, the little f of t must be equal to the cos of, well, what's b? This is 9, so that must be 3 squared. So if little f of t is cos of 3t, that would transform to be s over s squared plus 9. So this would be the big F, and this would be the little f. But I've multiplied little f by e to the at, because I see in here a s minus 2. So this must be f of s minus 2, not just f of s. So this would be multiplied by e to the at. Oh, wait, careful, there's an s on the top. So this should also be s minus 2. If the big F of s is s over s squared plus, in our case, this is 9, and this is 3. If this is our big F of s, then if I say f of s plus 2, I have to put an s plus 2 in everywhere there's an s. So this will untransform to be this where f of t is, okay. E to the 2t cos 3t will transform to be this piece. All right, so let's go back up to what we actually have. Oh, I wish this was a minus 2. So what I'm going to have to do then to make it a minus 2 is I'm going to have to go minus 1 plus 1 so that this minus 1 and this minus 1 can combine to give a plus 2. And I'm going to move this plus sign to here, and I'm breaking it up on that plus sign. So now when I common denominator add these two pieces together, the plus 1 and the minus 2 give me the original minus 1. And this piece, I'm set. That matches that exactly. That's going to unLaplace to be the e to the 2t cos 3t. We were expecting that when we thought about the eigenvalues. So if I was unLaplacing, I've got that piece done. I just need this piece. Let's look at the sine piece. If I were to, and our b, our imaginary part of the eigenvalue, if you will, is 3, so this should be 9. And I would like a 3 on top to match. If I multiply by an e to the 2t, again, I'm using this rule. Now, everywhere there's an s, that should put an s minus 2, because now the shifted version is where a is equal to 2. And now my f of t is my little f of t is sine of 3t. So this will unLaplace to be this. I wish there was a 3 on top. I'm going to put a 3 on top and a third on the bottom so it balances. And now I'm set to unLaplace both sides. So I've broken this up to match a cosine piece and a sine piece. You always match the cosine piece first, because the sine piece, whatever number that was on the top, it ended up being a 1. I can balance it. So you always match this cosine piece first. Now we're set to unLaplace both sides. The Laplace of y is f, so the inverse Laplace of f is y. This piece matches my e to the 2t cos, plus I have this third, and this, so a third's a constant, so that doesn't do anything with the inverse Laplace. That matches my e to the t sine 3t. Now I've taken the inverse Laplace, and this matches what I thought we would get, right? There was a constant here, c1, I guess the c1 is 1, and a c2, I guess the c2 is a third. This matches what I thought I would get. c1 must be 1, c2 must be a third. So what does that mean for us? The original thing that I had to unLaplace was s minus 1, and then this was all expanded out because we had to complete the square. So that was s squared minus 4s plus 13. So we looked at it, it was over a quadratic. We had to see if the quadratic factors or doesn't factor. It doesn't factor. So we completed the square and then lined up the cosine piece first, and then with the leftovers, the balancing leftovers, we lined up the sine piece.